Yeah, so this is the last part of gravitational waves, as I was saying. And what we saw the last time was really how this derivative, so these are the radiative modes, information about gravitational radiation is coded in these derivative operators D on sky, or more precisely, these equivalence classes of derivative operators. You are led to these equivalence classes because we have this conformal freedom. And these derivative operators satisfy properties, they satisfy some condition. In particular, they annihilate the metric. So they dA operating on the metric is equal to 0, and similarly dA operating on NA equal to 0. So dA of UBC equal to 0, dA of NB equal to 0, all on sky, all the equations hold on sky up here. These properties then imply that dA is completely determined by its action on one form LA such that NALA is not equal to 0. So just for definiteness, we take it equal to 1. And in terms of if scribe were embedded in space-time, you can think of this N as being a null normal to cross-sections of scribe. And so a convenient choice of this L, we saw, is that we can take scribe, which is S2 cross R, and then we can just choose a cross-section. This cross-section says C, or C not up here. And then given this NA, we can just drag this cross-section. So you get a nice foliation. And if in fact, if you have U as an affine parameter of N, then this could be U equal to U0, U equal to U1, and so on, these cross-sections. We get a whole bunch of family of cross-sections up here. And for each of these cross-sections C that I got here comes with a LA such that LA times dA equal to 0 for all tangent vectors dA to the cross-section. So any vector dA to the cross-section, then the statement is that there is a one form. This is a one form which is normal to this cross-section within SCRA. So we get that, and then with the choice, then it will follow that LA. We can just choose L on one cross-section such that LA and A just normalize it such that that is equal to -1, and then on some C0. Then that would just say that LA and A equal to -1 everywhere on scribe, and ln of L equal to 0. So these cross sections are lead drag by N, the L is lead drag by N, and we get this frame. And then some time ago when we did the peeling properties, we saw that I can also construct vectors N and M bar, which are tangential, and drag them, and I will also get a Newman-Penrose tetrad in that case, which is N bar, N and L up here on cross section. But at the moment, we're just looking at the scribe by itself rather than scribe being embedded in the physical space-time. So the important thing is that the D is completely determined by this DALA, and then the statement is that I can take this DALB and I can take its trace spring part, so QMN DMLN times QAB. This half is because the metric is 0 plus signature, so and this is what we call the shear. So this is shear of L, but I would not always write L. This is the shear tensor, and the statement is that the shear tensor is what characterizes our equivalence class. In other words, every derivative operator is completely determined by its action on LA. So therefore, DALB This will tell me what the derivative operator is, but two derivatives can be conformally related by a conformal factor, which is equal to 1 on scri, but its derivative is not 1 on scri. That just adds a trace term to this DALB. So if you remove that, then the equivalence classes of derivative operators we get, which are radiative modes. So this is the radiative mode. That radiative mode to which our derivative operator belongs is completely characterized by this sigma, and this sigma is symmetric. It is sigma is transverse to n, and sigma is traceless. And we saw last time that even though the metric is degenerate, its inverse has an ambiguity. But if there is a transverse, but sigma is transverse, therefore that ambiguity does not matter. I can choose any inverse here to say there is traceless. And if you like, this sigma is what one often uses, as we saw last time. Okay, so this is where we were, and now we would like to continue. And the point now is that basically, that if I look at the derivative operator, okay, now in fact, we did a little bit more last time. We saw that in fact, there is also, from the curvature, from the conformally invariant part of the curvature of D, we can construct a new tensor. So basically, the DADB, we construct the new tensor. So basically, you take DADB, any covector K on a scri, then this will be equal to the Riemann tensor, three-dimensional Riemann tensor, AD. And the point is that this is only determined by really the derivative operator D, because the metric is degenerate. And then this derivative operator D up here, sorry, this Riemann tensor up here has some symmetries, which says that this is completely determined by, let me get the sign right. By tensor S up here, this is completely, this determines the Riemann tensor. And this S with the downstairs indices is just obtained by lowering the index with a Q. So if you like going from this tensor to this tensor, we lose a little bit of information. But for the Bondi news, we just look at this tensor up here, and basically in the Bondi frame, we go to a Bondi frame just to kill the conformal freedom, and in the Bondi frame, then the statement is that new tensor is given by SAB minus 1/2 SAB QCD times Q. So that is the Bondi, and then the statement is that this is, I'm just stating these facts, that this is actually conformally invariant. So if you choose one Bondi frame, you'll get one answer. Somebody goes and chooses another Bondi frame. I told you that there are 3 parameter family of Bondi conformal frames, which make the metric Q on scri a unique to metric. So if we change this Bondi conformal factor of the Bondi frame in this conformal class, then the statement is that you're not changing this new tensor. And then what we saw was that the flux of energy and momentum through any region of scri. So you can take some region of scri up here, for example, this region of scri, let's call it delta scri. So the flux of energy through delta scri is given by integral delta scri times just NAB times du, and then d omega. This is just d2 omega, like this is just sine theta, d theta, d phi. You need to stay metric. And the flux of the momentum, PR delta scri, is just given by delta scri times alpha I. And these alpha is are the first three YLMs that I wrote down last time. So if you are interested in z directional, then alpha z would just be cos theta. In the y direction, it will be sine theta sine phi. And in the x direction, it will be sine theta cos phi times NAP. So one thing that you see immediately is that the flux of energy is always positive. This is a manifestly positive constant. And this really kind of resolved one of the key points about what are gravitational waves. Because the question was, are these physical, as I told you in the beginning, are these physical entities, or are they just coordinate effects? In one coordinate system, something may look like a wave. In another coordinate system, it do not look like a wave. And the question is, well, what is the physics here? And the point is that you can just calculate this Bond-in-use. If the Bond-in-use is not zero, then there are gravitational waves because they actually carry this energy away from the sources. So the sources, if you like, are in the interior, somewhere in the interior, inside the space-time, and I got the energies being radiated away, and that energy then passes through Scri up here, and that is the formula for Bondi energy. And this really was a key point in the debate that was going on about reality of gravitational waves in the early days of general relativity. By early days, I mean, almost 40, 50 years after the discovery of general relativity. I don't know if I mentioned already, but Einstein had already soon after the discovery of general relativity, a couple of years later, between 1916 and 1918, Einstein had written a couple of papers showing that there are gravitational waves in the linearized approximation. And what he did was, he just repeated the kind of calculation we do for electromagnetic waves. For electromagnetic waves, if you have a charge, but it's a dipole, so positive negative charge up here, and if it is oscillating, then the time rate of change of the oscillation of this dipole moment, you can solve Maxwell's equation with this oscillating dipole as a source, as you know, and then you can see that there is radiation that is going out. That is what is happening everywhere where we have Maxwell field. Right? I mean, the time-varying dipole moments are creating these Maxwell fields. So Einstein took a time-varying quadrupole moment of a source, and in the weak field approximation showed that time-varying quadrupole moment actually does radiate energy, and there are gravitational waves, and he highlighted this as a big difference from Newtonian gravity. But then, in subsequent years, there was a lot of confusion about whether there are gravitational waves in full general relativity because of the coordinate effects. How do you separate these things out? And it's very interesting because in 1936, I think, Einstein wrote a paper, or 35, 36, Einstein wrote a paper with Rosen, in which he thought he had proved that gravitational waves, in fact, do not exist in full general relativity, and that it was an artifact of the linearized approximation. And this is a very famous paper in which it was submitted to physical review, and then it came back with a 10-page referee report, which we now know was written by Robertson of the Friedman, Lemaitre, Robertson, Walker model, that Robertson, pointing out the error in the paper. And there's a big story that goes on here. Ultimately, Einstein actually, okay, so maybe people are not aware of this story, so let me just go and say it. So it came back from physical review. Einstein was completely, not happy because we have to understand the cultural context. In Germany, when he was the, member of the Prussian Academy, there, just like for the Royal Society, the idea was that Prussian Academy members went and read a paper and then it appeared in the journal. I mean, there was no referee process. And so he was very surprised that the paper was sent to a referee. He did not know that the referee process existed. Wrote a rather scathing reply back saying that to the editor, saying that I did not authorize you to send this paper to a third person without, before it was published. And in any case, the comments of the referee are erroneous. And anyway, I'm withdrawing it, and he submitted somewhere else. It's very interesting because the editor of Physical Review was a young person, and why he chose to do this shows great wisdom on his part, but it's not completely clear. Because the same year, Einstein had sent 3 papers. The first 2 of them, Einstein, Rosen, Bridge, Einstein-Rosen-Perovsky quantum mechanics experiment. Both of them were published without sending to a referee. But this was sent to a referee, probably because it said that something which was true in linearized gravity was not true in full general relativity. I mean, there was confusion about, and Einstein wrote a very clear letter to Max Born saying that with an assistant, I have now shown that gravitational waves do not exist in full general relativity, although they do exist in the linearized approximation, but that is an artifact of the approximation. In the full theory, there are no gravitational waves. So you can see how, I mean, it's Einstein, right? Not somebody else making a mistake. But then it turned out that by the time the paper, so he sent it to the proceedings of the annals of the Franklin Institute in Philadelphia, actually, and it was immediately accepted, and then he got the proofs. But between the time that the proofs came back, Einstein realized that there was actually a mistake, and we still don't know exactly how he realized it, that there was actually a mistake in the paper, and so he corrected it, and the final conclusion is completely different. That it is not that gravitational waves do not exist anymore, right? And these are the Einstein-Rosen waves that we now talk about. Rosen, on the other hand, until 1980s, continued to believe that the gravitational waves do not exist. So it was quite a, in other words, he did not accept that there was a mistake in the paper. By the time Einstein changed the proofs, Rosen had gone as a postdoc. Rosen was from Israel, he's a very famous Israeli relativist. He had gone for a postdoc in Soviet Union, so Einstein did not communicate with him when he actually made the changes in the proofs. And so Rosen was not happy about this, and he did not believe that gravitational waves exist until about 1980s. Conferences where you can see this being discussed. So you can see that there was a lot of confusion. And that is why in the 1960s, when Bondi and his group, and then later Penrose and Newman analyzed this and showed that in fact there is a gauge invariant notion of gravitational waves carrying energy, that was a big landmark. And I have to say that particle physicists couldn't understand this because they always just work in the linearized approximation, where of course it's clear that gravitational waves exist. The whole question was whether because of diffeomorphism invariance, that the notion of gravitational wave just loses its meaning. And this is what Bondi etc. showed. So Bondi, a remark that is attributed to him, his famous remark is that, yes, gravitational waves are real, they carry energy, and you can hit water with them. Which is of course not true, but I mean, which is true if you are sufficiently close to the source, but not when the source is very far away. So this really changed the whole paradigm, and since from the 60s, mid-60s on, then people took the gravitational waves very seriously. Now it looks ridiculous. How could people debate about this? But everything is ridiculous in retrospect. One needs clean framework to describe it. And you had asked me a question a while ago about why not do what we do in cosmology? And again, in the last part of the course, we're going to see what we do in cosmology. The reason is because in cosmology, everything is done only in the linearized approximation or in the weak field approximation. When we are not doing gravitational waves in full nonlinear general relativity, we're not talking about gravitational waves which are produced by inspiraling black holes, for example, which are very strong sources that are created. And to understand if gravitational waves exist beyond the linearized or beyond some kind of approximation, linearized or second order linearized approximation, in full general relativity, we needed this framework, and this is what clarified that gravitational waves do exist. Okay. Now, so we got this formula for energy momentum, and I don't want to go into angular momentum because it's much more subtle. As we saw for the angular momentum already at the level of symmetries, whereas the Poincare group has only 4 parameter family of Lorentz groups, the BMS group has infinite parameter family of Lorentz groups. It does have a unique translation, 4-dimensional translation group, therefore the notion of energy and momentum is well defined, but the notion of angular momentum acquires a new kind of ambiguity, or it has to be enlarged in a suitable sense, and that is much more technical, so I will not discuss that. We'll just stay with angular, with the linear momentum here, energy and momentum. Okay, so this is basically what we saw last time. Now what we would like to show is that in fact the relation between with what we did relation to the peeling. So early on, when we began gravitational waves, in order to make the analogy with electromagnetism clear, what I've done was I looked at the wild tensor. We used the field equations and the definition of the wild tensor and showed that the wild tensor had a certain fall off. And because Cry has a topology of two spheres, in fact, we had a peeling which said that psi 0, the component of the wild tensor, falls up as 1 upon r, psi 1 falls like, sorry, the other way around, psi 4 falls like 1 upon r, psi 3 falls like 1 upon r squared, psi 2 falls like 1 upon r cubed, and so on. We had seen it. And now what we would like to know is what is the relation between these derivative operators and the wild tensor. And the statement is that the relation is rather simple. Again, let me get the numerical factor right. So if I take, you see, in going from here to here, we lost some information because I'm lowering this index with a metric q, and q is degenerate. So this tensor has slightly more information than this tensor. And so the full content of the Riemann tensor in 3 dimensions is really in this 1-1 tensor that we got up here. So let us just look at that 1-1 tensor up here. So it has some additional algebraic symmetries, such as when I lower the index, what I get up here automatically satisfies SAB is symmetric, and it also satisfies SAB and B equal to 0, or if you like, even the SAB and B up here is proportional to NB, and so on. It has some symmetries. At the moment, these are not important, but let me just tell you that this tensor with certain symmetries is what contains the full information about this one tensor. These symmetries can be derived just from the proper fact that it's a curvature tensor. There's nothing new. I mean, I'm not using anything profound about it. It's that the derivative operator another is a metric and NA, and this is the curvature tensor of that derivative operator. From there, it follows that the Riemann tensor, because we're in 3 dimensions, there is no wild tensor, Riemann tensor of this form, where this S determines therefore the Riemann tensor completely, because this S is just a low index lower version of this S, and this S has some symmetry. Now, the point is that what happens, the Bianchi identities imply in the conformally completed space-time, they actually give you relation between this tensor S and the wild tensor. And what one can show is, this is just a fact, there are many things in here that I'm just telling you. We also did similar thing in the black holes towards the end of the discussion, because it will take too long to do it in class. It's not difficult. I gave references, and here also I give you references. So the Bianchi identities in space-time imply that in fact if I take epsilon AMN times dm, just take a derivative, like a curl type of derivative, d and b. If I take this, then this is equal to, actually, let me just call it star KB in space. So if you like here, this is a definition of star KB, but in space-time term, it is exactly what you expect. It is limit to Scri of omega to the minus 1 times C and B and M. So this is exactly what we call KAB CD tensor. We saw that from the space-time perspective, we saw that this wild tensor vanishes on Scri, therefore omega to the minus 1 times the wild tensor has actually a limit, and that is the limit that we call KAB CD. So the statement is that this derivative operator that determines this tensor D, this tensor S up here, and this curvature of the derivative operator. If I take another derivative, and if you like, this automatically skewed because of Mn up here, then this particular combination determines some components of the wild tensor. So what are these components in terms of the, I mean, you can just check it by just using the Newman-Penrose tetrad and making contractions. What the information in this star KAB is precisely what we call psi 4 naught, psi 3 naught, and imaginary part of psi 2. So these are 5 components. Of the 10 components, 5 are completely determined by this derivative operator. But this derivative operator is what represents the radiative mode. So if you like, these 5 components, they carry information about radiation. They are determined completely by the radiative modes, so they carry information only about radiation up here. So if you have stationary space-time, for example, these components will all be 0. There will be no radiation there. These components are all identically 0. Okay, so now the statement is that, and in particular this psi 4 naught up here, we saw that is psi 4 naught is equal to, this is the part of KABCD, physical KABCD, that falls off as 1 upon R, and this is what we call radiation field. Remember the Maxwell field, this was analogous, this psi 4 naught is analogous to the Maxwell field, phi 2 naught, which also was a radiation field. Okay, so psi 4 naught was the radiation field, and now therefore it is interesting to ask, we can write now the psi 4 naught, psi 3 naught, imaginary part of psi 2 naught in terms of this derivative operator explicitly, and I could write down the formulae, but the most interesting thing for us is psi 4 naught. And it turns out that is psi 4 naught. Remember what is psi 4 naught? Let's just write it first. Psi 4 naught is equal to at scry. I put hats now. The reason is because some quantities are in physical space-time, some quantities are at scry, so I put a hat. So evaluate this quantity at scry, which is KABCD times NA n bar B and C n bar D. So this was our psi 4 naught on scry. So this psi 4 naught is a function, it's evaluated on scry. So it is a function of u theta phi. So this is what this psi 4 naught is. So it just lives on scry here. And then one can ask, what is the relation with this derivative operator? In particular, we saw that the derivative operator can be expressed entirely in terms of the shear. What is this relation with the shear? So last time we saw that we can construct just the spin-weighted quantity that people generally construct, sigma naught, and that is supposed to be just equal to the shear, sigma AB, times MA and B. It has spin weight 2. And similarly, we can construct news. For some reason, people don't put a naught there, so I will not put a naught. News, which is NAB, NA and B. And then what we saw was that there was a relation between the two, namely, the news tensor is just the time derivative of the shear. So this is just equal to d by du of the shear. So we have got shear tensor, and its time derivative gives us a news. And the time derivative of shear tensor, therefore, tells us how much energy and momentum is carried by the gravitational waves. What about psi 4 naught? Well, it turns out that the psi 4 naught, just by definition, it has 2 m bars, so it has a spin weight minus 2, because it has 2 m bars. And the statement is that this quantity is just given by minus, that's out to be sigma bar dot naught. This is a complex conjugate involved because this has spin weight 1, this has spin weight 2, this has spin weight minus 2, so of course there's a complex conjugation involved. The sign is just various conventions about how psi 4 naught is defined. So we see that the first derivative of the shear tensor is the body news that really is carrying information about energy, momentum, and such thing. If the body news is equal to 0 in a space-time, then there is no energy that is carried by waves, by energy and momentum carried by waves up here. The space-time doesn't have any loss of energy momentum due to gravitational waves. And what we see now here is that the wild tensor component, which we call the radiation field, is just the first derivative of the news, the complex conjugate, or the second derivative of this shear up here. So now this is really important because what people do now in numerical relativity So binary black holes or binary compact binaries. Let me emphasize black holes. When we study compact binaries, so for example, you could have two neutron stars which are going around each other. Now, when these neutron stars are going around each other, or two black holes which are going around each other, so it's a certain system, physical system, and you can calculate the quadruple moment of this system. And because they're going around each other, the quadruple moment of this system is changing in time. It's basically because Maxwell field is a vector field. It's a spin 1 in physics language. Therefore, it is a dipole moment that is changing that gives rise to Maxwell field, the radiation of Maxwell field, or if you like, that emits photons, because photons carry spin 1. Gravitons or gravitational waves correspond to in perturbative quantum gravity. Gravitons corresponds to spin 2 particles, or radiative modes of gravitational field, also in a well-defined way, defined sense, have a quadrupole structure. So you need some quadrupole moment which is changing in time. Normally we think of a star which is oscillating and emitting gravitational waves, and that is correct. But it's also true that if I got these two black holes or two neutron stars, I can look at the total system, and because it is the orbit of the total orbit up here is such that the quadruple moment of the system is actually changing in time. Therefore, the gravitational waves are being emitted by conservation of energy. Then, in fact, the system is going to the two stars or the two black holes are going to fall slightly towards each other. This is a very slow process, but when they are sufficiently close, then it enters a nonlinear regime, and then the process is very quick. And therefore, these black holes and neutron stars finally coalesce, merge, and at that merger, there's a huge amount of gravitational waves that are emitted. I mean, typically, for example, that the very first merger that we saw, the total mass was about 60 solar masses of the two black holes, and about 2 or 3 solar masses were actually emitted in the form of gravitational waves. Now, E equal to mc squared is the energy that is emitted, and C is huge. Therefore, the total amount of energy that is radiated in this collision is absolutely huge. How huge? Well, at that, in the few milliseconds after the collision, the amount of radiation, amount of energy that gravitational waves carry outshines the amount of energy that is emitted by all stars in the entire universe via electromagnetic radiation. Solar mass energy is a huge energy. So 2 or 3 solar mass energy is really huge energy. I mean, what is happening near those in that region is a veritable tsunami, right? I mean, the space-time curvature is oscillating like crazy or something. But of course, luckily, this event is very far from us, right? This event, the first event that took place when Earth was still spawning first multicellular life. It was more than 1 billion years ago. And therefore, it was 1 billion light years away, and therefore, by the time it comes up here, then because of this 1/r fall off of the radiation field up here, the signal is very weak. But near the source, the signal is actually very huge. So what happens with these compact binaries? How do we analyze them? We use 2 things. We use numerical, analysis. When they are very far away, we can use weak field approximation in general relativity and use this so-called post-Newtonian methods. So these are, gravity is nearly Newtonian with corrections, and these are methods which are analytic, and we can use this approximation very well. Well, when they get close, then we have to use nonlinear full Einstein's equation, and therefore we use numerical relativity to analyze this. So what do people do? Well, people are typically saying that, well, you take a Cauchy surface, so if you like P equal to constant surface in physical space-time, and you have got these 2 objects, which are going around each other. So you want to give initial data here for these two objects. So the initial data will consist of the metric on this manifold, that we call HAB, the first and the second fundamental forms. So the metric and the extrinsic curvature on this manifold. This is the initial data. So this is symmetric. They satisfy some constraints. If they are black hole, then that's all we give. Now, how do I know that they are black hole? Well, I go and look for this initial data and find, in fact, that around here there are marginally trapped surfaces. So I got some bunch of region in which there are marginally trapped surfaces, and this is our boundary of black hole at an instant of time, if you like. And then we evolve this. We evolve this, then this is going to go into a dynamical horizon. But since they are very far in the beginning, in this region, they're almost like isolated horizons because they're not changing in time very much. There's not much energy that is falling into the black hole, but when they enter this regime, they become, it really is a dynamical horizon that we saw up here. So common dynamical horizon forms. So here I got two marginally trapped surfaces enveloping, and then finally we also have little marginally trapped surfaces around them, but there's a common marginally trapped surface that forms at a later instant of time. So t equal to t naught. At a later instant of time, t equal to t1. Actually, I got these two objects with little marginally trapped surfaces around each of them. But the important thing is that there is a common marginally trapped surface that develops. That is when the black holes are merged, when the common ones develops up here. And then the statement is that so this is actually obtained. I mean, the numerical relativity is needed somewhere big before the common horizon actually forms. And then this common horizon settles down. There's a lot of radiation that is emitted up in this region up here, just when the common horizon is formed, black holes are merged, and then these black holes settle down, finally, so they settle down to a curved black hole with radiation which is going out. Here also radiation is going out, but it's weak. Now the radiation is strong. This strong radiation, as it's going out, it is emitted. In the beginning, the marginally trapped surface that we have got has all kinds of multiple moments that I've told you about. It's very crinkly. As it loses radiation, it loses crinkliness, if you like, or sometimes one says it loses its hair, and it becomes smoother and smoother, and finally it just settles down to the curved dynamical horizon. So to begin with, the multiple moments are very complicated. At the end, the multiple moments are very simple. They are the curved multiple moments determined by just the mass and angular momentum. So this is a process up here that is happening. And so there is a final step up here after merger. We can again use linear theory, linear algebra relativity, but now linearization is about the final curse solution. So there is a post-Newtonian phase where the things are very far, then the merger occurs. Close to the merger and soon after the merger, we really need full-fledged nonlinear general relativity. And this is important, and this took a long, 25, 30 years to develop all the numerical methods and match them with mathematical theory of hyperbolic and elliptic differential equations and so on, and to extract information from it using, for example, notions of isolated and dynamical horizons. And then finally, we have got this merger, the post-merger phase, where again the black hole is just essentially curved, but is sort of slightly perturbed because of things that are falling into it, and it finally, asymptotically, it will just become curved. And this phase is given by the linearized phase. So I got these three phases. So what do people do then? The most interesting part of the signal, all of you have seen this LIGO signals hundreds of times by now. First starting about 2 years ago, right, when the first announcement was made. We had this press conference. NSF had the press conference, and we all met. Those of you who were here, we met in the mathematics building, in the seminar room there, where it was broadcast. It was broadcast all over the world. It was a very exciting event. And we saw this waveform. So what the hell is that waveform, right? What is that supposed to do? What does it have to do with theory? That waveform is just the sigma. So the waveform that is actually formed, that is actually plotted in this merger is this sigma. So what do we do? And please ask me the questions as soon as I'm done up here. What is it that is plotted? So you take numerical relativity, work on the space-time geometry, starting with this initial data up to black holes, and then we're looking at this psi4 plot. So there's a asymptotic wild tensor. This psi4 naught is, as we saw here, is the part of the asymptotic of the wild tensor that falls like 1 upon r in the radiation field. So that's what people actually extract, that actually they calculate. And from this psi4 naught, we can extract the shear by this equation that I got. Psi4 naught is equal to the second time derivative shear. And what is shown in these plots is this either psi4 naught or shear, typically shear. The waveform that is plotted up here is the shear. So, in terms of conceptual foundations or in terms of mathematical relativity, what we calculate is this. What happens in the live detector? Well, the waveform that extracts psi, and this is what is plotted to represent the waveform. From theoretical side, but from the detector point of view, experimental point of view, what we are plotting is strain in the detector. When the gravitational waves goes by, the detector arms are perpendicular to each other, and they're slightly contracted, slightly elongated, and then after in time, these oscillate, that oscillate in a familiar quadrupolar manner that you have seen in many books, your first course in relativity. So that is what is actually plotting. So the question now is, what is the relation between what is theoretically plotted, which is shear, with this strain? This is the question that we want to ask, and that is the last part that I want to do. And then I'll take questions. So for this, I have to make a little shift. And so far what we have done is, we are done, yeah.
Because you might be actually addressing it now, but I was wondering what the relation between shear is, if there's an easy relation between shear and the linearized gravitational.
Yeah, that's the next part.
Okay.
So that's what we're going to do. So I'm going to make a shift to talk about linearized gravitational field just for a second. This is also the way that I planned the course, because what we did was I assumed that you had taken first course in relativity, so you know about linearized gravity. So I didn't want to start with that and repeat it, but rather we're doing it the other way around. We're starting with full theory and then arriving at the linearized theory. This is also good because then it will make a smooth transition to cosmology, where one is using linearized perturbation theory. So I want to make a change the gears a little bit and remind you of linearized general relativity and gravitational waves in this theory. And then I'm going to come back and see what is the sigma naught in terms of this linearized gravitational field, exactly the question that Sina was asking just a minute ago. Again, let me get the convention straight. Well, I guess to begin with, so what we have is a background space-time. So this is like a D2 just for a second, and then we're going to make connection. Okay. So here we're going to background space-time, which is just Minkowski space. And what we were looking at is linearized gravity. And for simplicity, I'm just going to use no sources because we're interested in waves. If you're interested in post-Newtonian approximation, then sources are of course critical, but for waves, they're not critical, so let me not assume any sources. So what we do is the following. There are two ways of thinking about it. We can say that, well, I got a metric, GAB, physical metric, which is equal to eta hat AB plus some small parameter epsilon times gamma AB. Okay, I can say that. Or I like to think about it as really what we have is a one parameter family of metrics, which are all solutions to source-free Einstein's equations. At the parameter value 0, you have got the Minkowski metric, and then we're interested in the first order perturbation. So if you like, you've got a manifold of solutions, and first order perturbations are just tangent vectors at any solution in this manifold. So the statement here is that I just take d by d lambda of GAB of lambda and evaluate lambda equal to 0, and this is what we define to be gamma. So I can just calculate. Actually, these are different ways of doing it. With doing it this way, then you can go to any order you want. You can take further derivatives, d2 by d lambda squared, d3 by d lambda squared. You can go further approximations as you go along. Okay. So then the question is, what do Einstein's equations become? And again, this is something that I assume you have seen in your first course in general relativity, linearized approximation, and then the linearized Einstein's equations. So basically, you're taking d lambda of GAB of lambda. So GAB of lambda is always equal to 0 because our source is source-free Einstein's equation. So Einstein tensor always vanishes for all these metrics, and therefore I can take d lambda GAB of lambda at 0, and that gives me a differential equation on this gamma hat. And what is that equation that we get? Well, we get here this. We get this identically. So this is equal to 0, and what is this when you evaluate it? You just get this to be equal to minus 1/2 times log naught hat. Let me call it, too many symbols, but let me just do it. Gamma hat AB plus gamma naught B. So there's a bar and hat. Hat just means that they are physical space-time, and I'll explain what bar means in a minute. Gamma bar B, yeah. C minus 1/2 eta hat AB. So where gamma bar hat, we just trace reverse gamma. So this object is just equal to gamma hat AB minus gamma hat, which is minus trace. You just trace reversed. Sorry, there's a half factor. There was a half. That was wrong. Okay, so you just trace reverse in a minute. This is not going to be terribly important at the moment that it's traced reverse, because as you know, there's a gauge freedom. If anybody wants to know about this more detail, I will explain to you. But this gauge freedom just corresponds to gamma hat AB goes to gamma hat AB plus 2 times symmetrized derivative of any vector field. Or if you like, this is the same as d derivative of the metric eta hat AB. This just expresses the fact that diffeomorphisms are gauge transformations. I think most of you have seen this, right, in your general courses. So you using this gauge freedom in a source-free case, you can first of all say that impose gauge condition. In other words, we got this gauge freedom. I choose this zeta suitably in order to simplify the form of gamma hat up here, and then I can make gamma hat AB first of all spatial. So we got here Minkowski spacetime. I choose some t equal to constant surfaces. I got here t hat AB. T hat A is a unit time-like vector. So I just make only the spatial component of it non-zero, the space-time component 0, and I can also make it gamma hat AB, that is eta hat AB equal to 0. So this is traceless. So it is purely spatial and traceless, and this is often called the radiation gauge. Actually, I do two things. I should say first up here. Using this freedom, first of all, I can simplify the equation to use a Lorentz gauge condition. But gauge condition which says that grad hat D, gamma hat CD equal to 0. This Lorentz gauge condition. With this Lorentz gauge condition, then this term disappears. This term disappears because it's a flat derivative operator. It comes in, kills this. So I don't get anything here. I don't get it here. So I'm only then left with this 1/2. I'm just left with the equation, which is the wave equation. I should have said this before. Using this gauge freedom, we can first do this. It still leaves a gauge freedom where now zeta is a function of the wave, is satisfy the wave equation, and using this restricted gauge freedom, you can use the restricted gauge freedom to make gamma hat both spatial and trace free. Once you have done all this, satisfying the gauge, this gauge, the final outcome is that gamma, first of all, gamma bar hat A is equal to the same as gamma AB. Bar is the same as that because trace is 0, and the two differ from each other just by trace. So they are the same. And then, furthermore, the Lorentz gauge condition and this and furthermore it is spatial. So it has only indices in the space-like direction. And finally, the Lorentz gauge condition and this spatiality, they are just tells me that in fact it is divergence free. So in 3 dimensions, this tensor is actually divergence free. And of course, we already know it's trace free because we have imposed that condition. So in addition to that, gamma hat AB and AB equals 0. So finally, the statement is that the linearized gravitational field representing a source-free solution, that are waves, gravitational waves, they can be represented completely by a spatial tensor which is symmetric, which is transverse, satisfies this gauge condition up here, and is traceless. So this is all often called, as I said before, the Lorentz gauge. And then this condition up here is often called radiation gauge. This addition. The additional conditions are imposed up here using the restricted gauge freedom. Those are called the radiation gauge. So ultimately, I am in the radiation gauge and Lorentz gauge together, and then what I have is just here. I got a spatial tensor which is symmetric. It has 6 components. Okay, that's what it is. But it's transverse. So 3 of the components are killed. So I'm left only with 3 components. And finally, it's traceless. So I'm only left with 2 components. So this transverse traceless, so therefore gamma hat AB is often just written as gamma hat AB. Gamma hat AB, transverse traceless. So this is often the notation that people use, transverse traceless, and that is because all these conditions are satisfied. I know that this is a lightning review, but I think that you have all seen this several times, and so it's okay. Are there any questions? If people have not seen it and there are questions, please ask me now. Okay, so these are. Now what we can do is this is the linearized gravitational field, and what we would like to know is what is the relation between all these transverse traceless modes that I talked about here and the shear that I talked about here. Here, the full nonlinear relativity, the two radiated degrees of freedom are encoded in the shear. They determine, as we just saw, these psi 4 naught, psi 3 naught, and imaginary part of psi 2 naught. They give us the bonding news, they tell us how much energy is radiated and all that. So where is that information here? It looks like over here, again I got two independent components. There are two functions on a three-dimensional manifold because I'm looking at a t equal to constant surface. So I get two functions on these two independent manifolds. What are the two functions? They are just the components of the transverse traceless symmetric tensor field on this manifold. But at Scry, we also had kind of the components of sigma AB up here. And this sigma AB was symmetric, was transverse to Na, and it was traceless. Again, I got two free components, and here we also have two free components. But what is the relation between the two? You see, it's not obvious what the relation between the two is, and this again, people who do linearized gravity, it's important to understand this point. The reason why it's not obvious is because this decomposition, namely transverse, here where transversality means really divergence precondition up here. These conditions are very non-local. If you give me gamma hat AB on this three-dimensional surface, symmetric tensor field, and ask me what is its transverse traceless part, it involves a non-local operation which involves inverse powers of Laplacians, etc., to give you this part. If you like, normally it is done just by taking the Fourier transform. Right? You go to the Fourier space, and then this just says that the Fourier transform of gamma at AB is perpendicular to K. This is space-free. So this quantity is local in the Fourier space, but it's very non-local in the physical space. Whereas our quantity up here is completely local in the physical space. So at first it looks like, well, we're comparing apples and oranges. It's true, there are two transverse traceless modes, and then what is the relation between the two? And the point is that quite often people in the literature is full of standard books, Misnot-Wheeler, Poisson-Ville, various books, right? They discuss these transverse traceless things. And they have two notions of transverse traceless in the physical space-time. They don't refer to Scry. This is one notion, and then they introduce another notion which is just local in the physical space-time. That notion which is just local in the physical space-time, if you take the limit to Scry, you get this. But they basically confuse two completely distinct notions in the physical space-time and call them both transverse traceless. One is this, and then the second notion, which I have not written down, but let me just tell you that it is local in physical space-time, and therefore it's quite different from it. And that notion directly goes over to this kind of notion of Scry, because this is also local in physical space-time. But a nice surprise is that precisely because when you go to Scry, you go out to null directions. So I got some source up here, and radiation is going out here, and I got Scry here, and I'm going out in null directions up here. I'm going out in Scry plus. This is Scry minus. I'm not interested in Scry minus. I'm just looking at Scry plus up here. I'm going out in null directions up here. So as we go out up here, what we're doing is you're going along u equal to u naught, and then we can take this gamma hat AB, and I can do power series expansion. Of 1 upon r. So gamma at AB to begin with is a function of u r theta phi, and I can do a power series expansion in power of 1 upon r. And the non-trivial result is that, in fact, in Minkowski space, about which I am doing this linearization, the shear of L and also of N is identically 0, because this L is just a vector field which is just outgoing, it's just a pure expansion, there is nothing shearing, they are just light rays emanating one point. This shear is identically 0. But given this gamma at AB, we can calculate what is linearized shear. We can calculate what is delta sigma AB. So the shear with respect to eta AB is just 0. But shear with respect to the linearized metric, where I got this gamma at AB, is not 0. And you can actually calculate what it is. It's not a very difficult calculation, but you have to do it cleverly. When you do that calculation, what we find is that, in fact, the sigma, 2 times sigma up here, 2 times sigma up here, 2 times linearized shear, at sky. The linearized shear at sky turns out to be precisely gamma hat transverse traceless AB, where transverse traceless is this non-local operation in physical space-time that I've done. Okay, but still is that operation times n bar A bar B. So the point is that the 2 transverse traceless modes up here are precisely the ones in the shear. I'll say it once again, and then please ask me questions. What we did first is not worry about linearized gravity. We did just full general relativity. And we saw that the radiative modes are all encoded in the shear tensor, where the shear is calculated with respect to the vector field L that we got here. I generally suppressed it because we always use this with respect to the vector field L, or one form L on sky. So that is what. When we do linearized gravity, in the books you will see that one says that the radiative modes, the 2 modes which correspond to this deformation of a bunch of test particles going like that or like that. I cannot do it with the hand very well. The thing that you have seen many, many times. That is all done in terms of gamma. Then the question is, the full theory where I got shear, here we got the linearized metric, what is the relationship between the two? And the statement is that if you go to the transverse traceless gauge, and if I take the limit of this gamma, so I take the limit of this gamma at AB, transverse traceless, u theta phi, and I expand it out as something like not AB u theta phi divided by r plus something gamma 1 transverse traceless AB upon r squared, this again u theta phi, etc. I do a power series expansion of r squared, then the limiting field that I get is this is gamma naught. And the statement is that this gamma naught is the same as the shear in a very precise sense. Namely, if I extract the spin weight 2 quantity from here, then the spin weight 2 quantity from that is extracted from this linearized metric gives me precisely the linearized shear. Yeah.
So what happened? I guess what happened with this non-locality and locality?
Yeah. So exactly. So what happened with non-locality? So the statement is, I mean, we can. Right. This will take a while to do it properly, but if I take this surface like that, there is very non-local in this surface up here. This non-locality basically disappears, or if you like, this non-locality, this notion of transverse traceless just becomes this notion of transverse traceless in this specific limit. It's not true. You know, if I take a limit as you go t goes to infinity, then that non-locality is not going to disappear. At each time, there's going to be this non-locality. But if I'm taking the limit as u goes to u naught and r goes to infinity and do this power series expansion, it's just a mathematical fact that the two transverse spaceless modes that are there in the physical space-time, in the limit to Scri, become just local. And this is another beauty of Scri, actually, right? That's another way to say it. Things just simplify here at Scri. You can just do various operations in the physical space-time without having to go to the momentum space if you just live on Scri. So it's not a trivial statement, but it's true. I mean, it's not a trivial statement. It's clear because the books never discuss this, right? I mean, all the books have, there's a somewhat confused treatment about the transverse spaceless modes in the books. Yeah.
So you write delta sigma, delta with respect to what? So we compute sigma intrinsically at Scri. So
right.
What is this delta with respect to?
Right. So I got here one parameter metric GAB of lambda. G at AB of lambda. I do conformal completion, I get a one parameter matrix GAB of lambda. Each of them gives me sigma AB, but let me just say sigma at lambda. So I take dd lambda of sigma lambda equals 0. This is the linearized shear. This is completely determined by the linearized metric gamma at AB, because it's just the linearized shear. It is this linearized shear that I'm calling delta sigma. Okay. So if you like, or if you do the power series expansion, if you think of GAB as eta AB plus epsilon gamma hat AB, then I'm given this matrix, but of course there will be, I'm given this matrix up here, and then I'm just looking at keeping terms only linear in epsilon in the calculation of sigma. The term, so this metric has some sigma, that's Scri, and I'm just keeping the terms which are linear in epsilon, and that is what I'm calling delta sigma. I had to do this because I'm just comparing what happens in full theory with the linearized theory. So obviously I had to linearize somewhere, and I'm linearizing here, and this is the linearized metric up here.
That equation is just linearization of the Bianchi identity, right?
With this equation?
Yeah. Is that true?
No.
Okay.
It's not a Bianchi identity. It's just it's a fact about the solutions to linearized solutions to Einstein's equation as you're taking the limit. No, it's not something trivial. Okay. It's something really has to do with this amalgamation of two things, namely this is the notion of transverse spaceless, which is very non-local and such thing up here. But I'm taking a certain limit. I'm taking a limit as u equal to u naught, and then keeping the leading term in R. So that is the statement that is that. So it doesn't come from Bianchi identities. It really has to do with this detailed thing that we did, which has to do with fixing a certain gauge, doing things, and so the modes that are extracted here, the physical space, these are extracted in the physical space-time. But at infinity, they become the same as the modes which are extracted at Scri. And as you said, it's a highly non-trivial statement because at Scri, it is all local means it's a boundary, but still it is local in space-time, whereas at each instant of time t, it is extremely non-local in space-time. It is because this limiting procedure drops the non-locality and expresses and allows me to express something which is intrinsically non-local in physical space-time in terms of local things at Scri. You have a question, Martin?
Oh yeah, that's.
Okay. So the statement is that it is this linearized metric that is captured in sigma, and I think again I just leave to you that you saw this in the first course in general relativity, that when you studied linearized metrics, that when we got this linearized metric solution, that is a solution that given a ring of circular test particles, that's better way to do it, given a ring of circular test particle, you got this mode, and the other mode, which I cannot do with my fingers, and we got this other polarization mode. Those modes are all done in terms of this gamma. The same modes appear in terms of the sigma because of this non-trivial relation between full nonlinear general relativity and its linearized approximation. This exists in full nonlinear general relativity. I don't have to use any linearized approximation. This, of course, is the linearized approximation. Yeah.
Yeah. So you said that the numerical relativists plot the sigma naught, but that depends on a gauge choice of m, right? So what do they?
Right. Very good. So, yeah. So we had, that's a very good question. So in the whole construction, we had to construct Newman-Penrose tetrad. And all of these things have to do with, do we have the right Newman-Penrose tetrad? So that really refers to having this, as you saw before, to construct the tetrad, you got scri and I need a cross section. Once I got cross section, I can do all that. So the question is, where is this cross section coming from? So the point up here is that, conceptually, what is happening is that in this phase, when things are very far away, very early times, or in this phase, at very late times, the radiation has died out. When the radiation has died out, you do get these cross sections which are zero shear. Okay. There are cross sections which are shear, but if I just wiggle that cross section, it is not zero. There exists cross section with zero shear. If it's sigma dot is equal to 0, nu is equal to 0, and radiation, then there exists cross section which are equal to 0. So we can take these cross sections which are shear free, either in the future or in the past, and then once you give this cross section before the burst of radiation comes, say for example, and then, or after the black hole has settled down, and then the statement is that you can construct a Newman-Penrose tetrad associated with, once you give me a cross section, then I know how to construct a Newman-Penrose tetrad. And that is a Newman-Penrose tetrad that they are in principle computing. What I'm presenting here is what is the mathematical and conceptual basis of what they do. Of course, when they actually do things, they use many approximations further. They cannot go all the way to scri, they go to a sufficiently large radius where 1 upon r can be extracted numerically because 1 upon r squared is sufficiently small that you can ignore it, or if you like, you work with some in that approximation up here. So there are additional approximations that are coming in which you have to stare at and see that they are okay, but of course, they've studied these things, so they know how to extract these waves, and there's a lot of, it was confusing in the beginning, but 30 years have passed, people have studied this in great detail, they know how to do it. But conceptually, what one is doing is really waiting until all the radiation has passed away, then I know what good cross sections are, shear-free cross sections are, and then use a Newman-Penrose tetrad based on those cross sections, and then that is what is called plotting in terms of shear. Abhay?
Yeah, I am not understanding something. Maybe I'm missing something stupid. So usually the shear is somehow the derivative of the metric, right? But in the expression delta sigma that you have, because the 1 upon r, okay.
Yeah, it's very confusing. It's very confusing. Your point is extremely confusing, but it's because of that 1 upon r. That is what takes care of that.
Sorry, this identification between sigma and gamma requires the use of Minkowski at scri class?
Yeah. Or stationary space-time, but I'm just using Minkowski for.
So
I could do stationary space-time, but
okay.
But people almost always do this transverse spaceless decomposition in Minkowski space in every book and such thing. They don't do it on a stationary space-time. That's why I didn't want to go into that thing.
So in this language, we are in Minkowski
right.
when we are looking for this.
Right. In this language, we are in Minkowski space-time. We're sufficiently far away. And that was really related to the question he was asking, which Minkowski? Well, we are in that Minkowski which is selected by what happens in the distant future. So what happens in the distant future is really stationary space-time, but that stationary space-time is the same as Minkowski space-time. As I said before, I could do everything in stationary space-time, but just to make contact with what is there in the books, I'm making a contact with what is happening in Minkowski space-time.
Physically, there is happening something. We have a detector. We are in Minkowski, so morally we are in scri.
Yeah, morally we are at scri.
And then we can match.
Right. We're sufficiently far, and not just because of Minkowski, but we're sufficiently far from the source so that we're in the radiation zone with respect to the. If something happened in the solar system, of course it would be destroyed completely, but we could not use this description. Okay. So I'll stay here. I know people have to go to classes. Those of you who want to see me, we can meet afterwards because those were classes. But we're done with the gravitational waves, and I want to begin next time completely fresh with cosmology, but we'll make kind of a contact with these gravitational waves, this linearized theory, when we go to cosmology. I need to know a couple of things from you. First is, how many people here are familiar or are familiar with the, it's the standard Friedman, Robertson, Walker cosmology? Everybody is familiar, great. How many of you are familiar with quantum field theory in Minkowski spacetime, just creation, annihilation operators, etc.? Okay, very wonderful. Okay, and then the last question was, how many of you are familiar with cosmological perturbation theory? Not everybody.